Hello and welcome to the Sumo Logic Threat Labs Learning Channel. I am Julian Crowley, Team Lead of Threat Detection Engineering for Sumo Logic Threat Labs. In this instructional video, we will be exploring the intricate world of Sumo Logic log parsers. Specifically, we will be delving into parser templates that have been created to help Sumo Logic users get a quick start on developing parsers for common log formats. The first parser template we'll cover is for JSON logs. This section will also cover some general guidance applicable to parsers of other types. Note that each parser template is available out of the box with comments and without, so they can be reviewed, duplicated, and modified as needed. JSON is one of, if not the most common format we encounter for modern applications. Mercifully, as a well-understood structured format for logs, most parsers for JSON logs are relatively straightforward. There are some circumstances, even in JSON, however, that require a slightly more complex parser to handle appropriately. We'll cover some of these circumstances here. The majority of parsers will begin with a parser stanza at the beginning to define what format the data comes in. For this example, we only have data stored as JSON, so begin this parser stanza with format equals JSON. There are some cases, such as JSON forwarded logs over syslog, where a pre-parser is needed to process a header and then pass the JSON body of the message along to a parser for that component of the log. Next, we define the mapper attributes. These are set to allow the corresponding mapper to know which parse logs to route to which mapper. These attributes are vendor, product, and event ID. Typically, these will be set once in a given parser, as they are in this example. However, there are circumstances that may require setting these multiple times in a parser if you can expect a highly diverse set of logs to be parsed by a given parser, such as in log streams that contain multiple products with which each define their event IDs differently and merit being parsed separately. To reduce parser complexity, it is best to avoid trying to parse too many different log formats or variations of data in a single parser. Typical delineation is one parser per product per format type, but this is not required. With mapper attributes set, the next set of attributes likely to be shared across any logs hitting a parser will be time. Start time field determines where from a log or from metadata the timestamp will be parsed. Time parser instructs how that timestamp will be read. In this instance, we're using the metadata field message time, which is created upon ingest of the data. There are some advantages to using message time, if there is no time zone information included in the log, for example, if the time zone format varies unpredictably, or if you simply don't want to deal with determining which is the correct timestamp parser to use. The collector is capable of auto-parsing time from the log in many different formats and can set time zone per source, or can just use the time the log was received. Message time can be a simple bypass of having to worry about time. A disadvantage of using message time is some logs contain multiple timestamps. The collector auto-parsed time will pick up the first timestamp it finds if not instructed otherwise. An important note, as collector metadata is not present in pasted log samples or in the log search conducted from the parser UI, message time will not be accurately reflected in the parser test. Most often, a JSON log can be fully parsed simply by defining the format field as JSON as we did above. However, if you look closely at the example log, there is a field within the JSON which contains nested key value pairs which contain valuable information worthy of separate parsing. Since all the data from the JSON is parsed initially, we now only need to reference the field name which requires further processing. This uses transform, then a colon, then the field name is parsed, then the name of the transform stanza, which we will apply further processing. Once that is called, the field we are processing further can be dropped. Key value pairs can come in many different forms. Key and value can be delimited in different ways. There may be quotes around the values, or some values may have different rules for when they are always an unbroken string with no white space, and for strings with white spaces. For these reasons, we use a regular expression to define what format the key value pairs take. In most cases, the format key value pairs takes is predictable enough that we can define the pattern once and instruct the parser to perform a repeat match. We use $$field_1 and $$val_1 as variables. When combined with repeat match, the key name is captured from the log with the corresponding value and repeated as many times as necessary until all key value pairs are parsed. This saves a lot of time and is significantly less brittle, as you will only need to define the pattern once and don't need to know the key names ahead of time, only the pattern that they take. With each component of the parser now in place, we can review the parsed output, though realistically this would have been done throughout the parser development. We see now that the main body of the message is parsed using the initial JSON parser and the nested key value pairs by the key value pair stanza. Key value pairs can be found across a wide variety of log formats and products. While structured formats like JSON have an understood structure so they can be parsed by defining a format, the structure of key value pairs can vary from product to product. In this section, we'll cover a few common scenarios to assist in parsing key value pairs from a log. Note that each parser template is available out of the box with comments and without, so that they can be reviewed, duplicated, and modified as needed. The majority of parsers will begin with a parser stanza at the beginning to define what format the data comes in. For this example, we define the parser format as regular expressions, regex for short. In the example log, we have header information that differs from the main body of the log message. To properly process this message, we'll need to first parse the log's different pieces. If you have a consistent header where the timestamp, any product information, or other components are consistent or at least somewhat predictable, you can create a regex pattern first to extract the different pieces of the log before the key value pairs are extracted. Here, timestamp header and the body of the message containing the key value pairs are captured separately. We use the parser internal variable starting with a $$ to capture the body of the log into a field that can be reused but won't be visible in the parsing dictionary. A similar result can be achieved using drop when you don't want a field to appear in the dictionary or be available for further processing, though you can still have a field you wish to drop be processed by calling the transform before the drop. With the log broken into its components, we can then call a transform for our $$ log body and specify the transform name after the equal sign on the transform, in this case, parse key value. Before we go to the key value transform, we can now specify how time will be handled in the parser. If you are using a timestamp from the log itself, you must specify which field to take time from in the start time field. Since we parse the header and it contained the timestamp, we have the timestamp field available in the field dictionary already. With the field specified, we can now define what format the timestamp follows. This uses Java timestamp formatting. If you know you can have multiple time formats for the logs processed by a given parser, multiple time formats can be specified in the time parser field by separating each format with a comma. With header and time handled, we can now address key value pairs that appear in the log. In this example, there are several different forms that key value pairs take. Each have the same delimiter between key and value and are double quote delimited values, but the keys and values can have spaces. Both variations need to be accounted for in our regular expression pattern. Instead of creating a long regular expression to parse each key value pair in the log, we can instead define a single pattern that will match on each instance of a key value pair. This has several advantages. First, it reduces the time it takes to create a parser, but also allows for variation in the number of key value pairs represented. So long as the pattern continues, an arbitrary number of pairs can be parsed. To accomplish this, we use the internal variables $field1 and $value1 to define the key and value parts respectively. These will take on the names and values from the log. Next, repeat match tells us to run over and over until all pairs have been parsed into the field dictionary. After the key value pairs have been parsed into the dictionary, we only have to define mapper metadata. In this example, vendor, product, and event ID are all defined statically. Mustache templates using double curly braces can be used to use parsed fields from the dictionary for each of these as well, if desired, though typically only event ID uses these. With each component of the parser implemented, we can review the field dictionary to verify that all desired fields have been parsed, time has been set by comparing the timestamp from the log with the parsing time to verify, and mapper metadata is properly captured to SIEM mapper fields. Common Event Format, or CEF for short, is a structured log standard developed by ArcSight. We'll cover a few scenarios that you may encounter with CEF here. Note that each parser template is available out of the box with comments and without, so that they can be reviewed, duplicated, and modified as needed. The majority of parsers will begin with a parser stanza at the beginning to define what format the data comes in. For this example, we define the parser format as Ceph. Since defining the format will extract all key value pairs and header data, we can define the mapper metadata right away. Since the pipe delimiter header for Ceph is standardized, it is possible in some cases to use mustache templates for vendor, product, and event ID. However, since we recommend having individual parsers for unique products, it is most likely vendor and product will be defined statically per parser. Ceph also has standard time fields. In this case, we use RT for receipt time and define the time parser following the format that appears in the logs. While Ceph has a predefined schema, it is also extensible. These are shown in two possible formats, CS for custom string and CN for custom number. The value and keys for these extension fields are separate key value pairs in the log, using the pattern CN and CS digit for the values, with CN and CS digit label for the corresponding key names. Since this is a known pattern, the key value pairs are automatically constructed. However, the original key value pairs from the log remain. Since these are extraneous, we recommend dropping these fields. Again, as they adhere to a pattern, we can construct a regular expression to handle dropping these fields without having to drop each explicitly. With all key value pairs and mapping and time metadata defined, we can review the field dictionary to ensure everything is parsed and metadata defined appropriately. Log event extended format, or LEAF, is another structured log format similar to Ceph. It was developed by QRadar. We'll cover a few scenarios that you may encounter with LEAF here. Note that each parser template is available out of the box with comments and without, so they can be reviewed, duplicated, and modified as needed. The majority of parsers will begin with a parser stanza at the beginning and define what format the data comes in. For this example, we define the parser format as LEAF. As with Ceph, defining the format will extract the header and key value pairs from the log. These can be immediately used for defining the mapper metadata. Since the pipe delimited header for LEAF logs is standardized, it is possible in some cases to use mustache templates for vendor, product, and event ID. However, since we recommend having individual parsers for unique products, it is most likely vendor and product will be defined statically per parser. LEAF also has standard time fields. In this case, we use dev time for device time and define the time parser following the format that appears in the logs. LEAF may define a dev time format field in the timestamp if it is not in epoch time. This can be used if needed to construct the appropriate time parser. In this example, epoch time in milliseconds is used, so no separate format field is necessary. LEAF is similar to Ceph in that it is extensible. However, extension fields in LEAF do not follow the same pattern of defining values and keys separately as in Ceph. Instead, key value pairs are represented the same way as fields in the LEAF schema. As such, there is no need to drop extraneous fields from the parsed field dictionary. With all key value pairs and mapping and time metadata defined, we can review the field dictionary to ensure everything is parsed and metadata defined appropriately. CSV, or comma separated value, and other delimited separated value logs, other than a comma, are another structure we observe frequently. Here we'll cover a few common scenarios you can encounter with these formats. Note that each parser template is available out of the box with comments and without, so they can be reviewed, duplicated, and modified as needed. The majority of parsers will begin with a parser stanza at the beginning to define what format the data comes in. For this example, we define the parser format as CSV. Since the CSV format is configurable for what delimiter it uses, the default being a comma, we first define that delimiter with field delims. The delimiter character is wrapped in double quotes. Here we use a space, as example logs are space separated. Next, we define the delimiter characters of the headers. That is, the key name that each value represents. Once again, this is wrapped in double quotes, and the delimiter for the headers is a comma. With delimiters and header delimiters defined, we can now provide the header names for the values in the CSV. Remember that these values are separated by commas as we defined in the field header delimiters above. Many CSVs have some variability in the number of fields that are present. These can be handled using optional fields, which has a similar structure to the above fields, but each additional field is itself optional. This is useful if you have possible fields that may appear in a CSV in a certain order, but you don't necessarily know how many fields may appear in a given log. If you have all possible fields that can, but won't necessarily appear, use optional fields to define those. With the core and optional fields defined, we can now select where time is parsed from in the dictionary. Here, the start time field is used for start time field, and by counting the digits, we can determine this as epoch time in seconds, which uses x1 for time parser. CSV formats do not always have an identifiable event ID in the actual log message. So here we define the event ID along with vendor and product statically. To use a field from the parse log, define that using double curly braces around that field name. With each component of the parser implemented, we can review the field dictionary to verify that all desired fields have been parsed. Time has been set, again comparing the timestamp from the log with the parsing time to verify, and mapper metadata is properly captured to SIEM mapper fields. While it is becoming less common, there are still myriad data sources which produce logs in unreliable structures or without any structure, and as such cannot be predefined. For those formats, we rely heavily on regular expressions. So for the parser stanza, we use format equals regex. In some cases with unstructured data sources, there are at least components of the log which follow a predictable pattern. For this example, we are using Cisco ASA logs as they contain a header which largely follows the same pattern for each log. We start by parsing this header to break the message down into its individual components, and to help determine what should happen to each unique message pattern. Here, event ID is what differentiates each message from each other. With each corresponding event, there may be some variation, but they mostly follow a predictable pattern. We use event ID in a variable transform to route messages parsed in the pre-parser to the appropriate parser for that event ID. But first we must define the event ID as the index field for the variable transform. In variable transform index, we have the first field we wish to have further parsing applied to it, followed by the field to be used as the index, in this case, event ID. With the log field and index field defined, we can now route messages with the specified event IDs to their appropriate parser. Each line represents a separate variable transform for each event ID from our examples. The event ID itself comes first, followed by the name of the parser transform to be applied to the messages with those event IDs. There is no explicit timestamp in the body of the log message, only that added by syslog. Since the format the syslog timestamp follows is configurable, it is recommended to use message time and allow the collector to auto-parse time and allow the parser to use that timestamp. As message time is represented in epoch milliseconds, we use x1000 as the time parser. Before we get to the individual parser transforms, we need to define the common metadata each message will receive. In this example, we use Cisco and ASA for the vendor and product, with the event ID templated as it should be the only component likely to be variable in the mapping step. In this example, we have a transform for each message defined by their respective event IDs. However, you can use the same transform repeatedly if the messages follow a pattern that will match the regular expression defined in the transform. It is generally recommended only to do this if the message to be parsed follows a very similar format and has a similar meaning. Breaking each message in a given pattern out can help make troubleshooting and expanding parsers simpler. For each transform, we are also leveraging out-of-the-box patterns. These are shown with a %sign followed by a pattern type and the key name wrapped in curly braces. These can be useful as shorthand for complicated patterns like an IP address and make reading the regular expression easier. With all the key value pairs and mapping and time metadata defined, we can review the field dictionary to ensure everything is parsed and metadata defined appropriately. Increasingly uncommon, having been supplanted by JSON, XML is another structured format logs can come in. Since it is a well-known structured format, we can specify that format in the parser stanza as XML. With XML, there is some additional complexity to parsing than we see with JSON or other structured formats. Since we want to parse everything in the example XML, we use parse all tag and specify EPO event from the example, which encapsulates everything in the log. However, the nested structure of fields could lead to a lot of repetitive strings in the field dictionary. To avoid this, we can specify the tags to ignore. The top-level tag, EPO event, is redundant in this case, as it doesn't provide any context we don't already have. As such, we can use ignore dictionary tag to strip the tag from the field dictionary while still parsing everything beneath it. With the tags to parse and extraneous tags to ignore complete, time parsing can be set up. In this example, we have an event timestamp written in GMT time. Start time field can use this paired with the correct pattern in time parser. With the log parsed and time set, we can define mapper metadata now. Here, vendor and product are hard-coded with event ID leveraging the event ID field from the log using the mustache template. Finally, with everything parsed and both time and mapper metadata set, we can review the parsed output to ensure everything has been parsed properly. While out-of-the-box support for Windows XML is already present, since this is a distinct structured format supported by our parser engine, we'll cover an example of this parser should there be a desire to develop custom Windows Event Log XML parsers apart from those included out of the box. First, we specify Windows XML as the format under the parser stanza. Next, vendor, product, and event ID metadata are defined, while the out-of-the-box parsers join channel and event ID to formulate an event ID for our built-in normalization mappers. Here we use provider name as the starting point, as to be more generalized. With mapper metadata set, the only remaining piece is to set how time is to be parsed. Here we'll use system time from the log and the corresponding pattern for the time parser. Finally, we can review the parsed output and verify everything is parsing as desired. This concludes the overview of Sumo Logic log parsing templates. Feedback on these parser templates and instructional content is always welcome. Thank you for watching.